Okay, so we have discussed swing equation. We have discussed swing equation. After that, we linearize it, apply to steady state stability. Or I would say small signal stability. Small signal stability. Today we will discuss transient stability, which is also known as large signal stability. So make a heading in your notebook: transient stability or large signal stability. Evaluation of transient stability is a phenomena which occurs before the fault occurs, right? Any system, first we need to estimate whether the system will be stable when faced with a fault or a large scale change. We are actually estimating. So any transient stability study is basically a power system study. Not exactly you will apply a fault and then you will study. It's not like that. You estimate by modeling the system. Okay. So what are the steps? First is you will determine the initial pre-fault state, just like you do that alternator three-phase short circuit. So pre-fault means 200 volt connected to synchronization. What is the current? That is pre-fault. Then initiate the fault. In our lab, you do the sudden short circuit. Compute the post-fault transient motion. Just like in case of synchronous generators, we see a curve like this, right? No, not this. In fact, large deviations and it stabilizes. Okay. And this is stored in a storage oscilloscope because this happens when it is small time. If these forces do not exceed the breakpoint of the strings, here we are considering the power system to be connected, some blocks connected by strings. So you are simply putting too much pressure on the balls. So if the strings do not break, that means the generator do not get desynchronized. That means the system is stable. Okay. Now in the next class we will discuss what is that limit, known as critical clearing angle and critical clearing time. So that is the limit. Just like if we are doing some exercise in the gymnasium, you can lift some weight. Okay, so you can hold it for some time only. Okay, so there is a critical clearing time. The person who is helping you must take out the weight. Okay, otherwise you will damage your body. Right. Similarly, synchronous generators can handle faults only for a certain duration. So before that, circuit breaker must operate. Otherwise, it will be desynchronized, become unstable. So synchronous generator systems are generally known as elastic energy systems. The rotor position to experience transient deviation. It can be asserted by analysis. So we are actually doing, so when it is a transient stability, we are analyzing it. We are not exactly putting a fault on it. The individual rotor angle will settle down to a new post-fault steady state, okay, corresponding to a new equilibrium state. So I told you, after small signal stability, the rotor shifts with small angle delta. But when there is a fault, that shift may be very large. And what is that shift the generator can make is known as critical clearing angle. Okay, maximum angle before which the circuit breaker must operate. The accuracy with which we can predict the post-fault rotor swings is intimately connected with the accuracy of the dynamic model. So what is the synchronous machine equivalent circuit? Synchronous generator equivalent circuit not. You have a generator. It is connected to a reactance, to the grid, synchronous reactance. It has a synchronous generator or equivalent model. Transformer what? Primary side, secondary side. You refer that to primary side, that is transformer equivalent circuit. Induction motor equivalent circuit similar to transformer. Stator side, rotor side. And you can transform that to stator side. Okay, that is how you do the analysis. But for synchronous generators and motors, the equivalent circuit is very simple. You have a voltage source, a reactance corresponding to the winding. This represents the winding. This represents the winding of the machine. We generally ignore the field. When we say equivalent circuit, we don't show the field. Okay, so this is the electrical equivalent circuit. But this is a static model, steady state model. It's a static model. Okay, so you need to understand the dynamic model. You need to get the dynamic model. So when you do a proper fault analysis for a synchronous machine, the dynamic model must be accurate. Now, what dynamic model of synchronous machine you know? Static model, you know this from machines subject. This was taught in machines. You might have read like Vt is equal to E minus Ixs or Ixs. Like you might have read in your machine. That's known as machine equation. Okay, voltage equation. Now, what is the dynamic model?
Dynamic is
static. Dynamic model is the one which will show you how the rotor angle varies with time. So what is that equation that shows you the variation of rotor angle? We had the complete class on that. That's known as swing equation. Okay. So for our purpose, swing equation is the dynamic model. But it's not exactly a completely accurate model. But for our purpose, at your level, swing equation is a sufficient model. But if you are doing research, it's very saturated area now. So people have already done research, so much research in the dynamic model of the synchronous machines. So you have several models available, dynamic models, on which you do transient stability studies. Okay. But eventually the objective is to know how much the delta is expanding. Whether it can come back below 90. Okay, that is the whole objective. All faults are symmetrical in transient stability studies since they are the most severe contingencies but require least complicated analysis. Fault analysis we will revise again in module 4, but you have some idea. So we have got one is known as triple line to ground, right? The other are unsymmetrical fault. This is a symmetrical fault. Unsymmetrical faults are line to ground, 9 to 9, double line to ground, right? So these are the unsymmetrical faults. This is the symmetrical fault most severe because 3 lines are connected. Now what is the percentage rate? 10%. This is 90%. Right? These faults. And these faults combined are known as shunt faults. Right? These are shunt faults. What are series faults? Breaking of the conductor. Have you seen any conductor in the transient line breaking somewhere? You lecture? Never happens. Very rare. We can have sag, swell, sag of the conductor, but breaking of the conductors, they are very strong. They don't happen. Unless there is some physical phenomenon like earthquake or something like that, then they may break, but it's very difficult for the conductor. The pole may break, the conductors won't. Okay, right? So series faults we don't bother about. It is the shunt faults we are concerned about, and among the shunt faults, most common are the line to ground faults. Only line to ground. But for transient stability study, we use 3-phase faults, not line to ground. Why? Why? Kind of line to ground to so common. Triple line to ground to analysis. Kind of. So severe. When we want to test whether our system can handle contingency, then we push it or put it under the most severe fault or severest of the fault. That's why all the transient stability studies, they do the fault analysis under 3-phase faults. And the good thing about that is 3-phase faults are the simplest because they are 3-phase symmetrical. They can be analyzed on a single phase basis. For unsymmetrical faults, you need to draw sequence networks. Once you will do positive sequence, then you will create negative sequence, then zero sequence, connect them, find the current. Okay, so we don't go about that. So it's a easier method. The individual power angle dynamics of each generator follows the second order differential equation or the swing equation, which is our model in this case, dynamic model. Coherency assumption doesn't apply unlike the control area and low frequency dynamics. You will see that in the fifth module. For all practical purposes, you can consider the static position to be steady state. And the lines transformers should not bother. Individual generators will be described by differential equations which are mutually coupled by power flow equations. So in a transient stability studies, the generators have swing equations. They have swing equations, but transmission lines we consider steady state. So they are simple load flows. So what is how to go forward towards analyzing the transient stability? Transient stability study means you solve this equation to obtain delta versus T. That's it. The analysis of transient stability means that you solve this equation to obtain delta versus T under fault condition. That's it. Okay. It may appear to be very simple to obtain delta versus T, but this is very complicated given the synchronous machine dynamic model is complicated. The actual accurate model is complicated. So it's very difficult to solve this second order differential equation. Okay. So therefore there are several numerical methods available, of which we will see only one, step by step method or point by point method, which you are actually plotting in your lab when you do fault analysis. That is the Scilab code on which you are plotting the generator angles. You are actually solving the swing equation using a numerical method known as step by step method. Okay, that code is there. Okay. No closed form of solution exists for swing equation except when the mechanical power is zero, which doesn't have any meaning, which involves elliptical integrals. So we go for numerical methods. Okay. For small perturbation equation and linearized, which we have seen, and we have found out that for a system to be small signal stable or steady state stable, synchronizing coefficient must be greater than 0. A generator must respond to load change. That is what is required. The practical approach to transient stability problem is to list all contingencies and do it. And the final solution is numerical solution of the swing equation is then obtained in the presence of the above disturbances, giving a plot of delta versus T. Okay. The last line is the answer. What transient stability gives you? It says list all the contingencies, okay, mostly the three-phase faults that are appearing on the circuit. After you apply the circuit fault, then find out the delta versus T. Okay, we'll see problems in the next two classes. We'll see how it is done. One problem is already you are solving it. Okay, I have sent you the updated manual for load flow. Right? Shared that load. Fault analysis, transient stability lab experiment, updated manual I have sent it. Okay, earlier manual there was some problem, I have sent it. Go through that. There it is shown how the swing equation is solved numerically. And code you already have. Next. Upon occurrence of a serial disturbance phase short circuit, the power transfer between machines is greatly reduced, causing the machine torque angles to swing relatively. Why power transfer between the machines is reduced? Because the power goes down the drain, right? It goes to the ground. So it's the ground fault. Goes to the ground. Instead of going to the other machine or other loads, goes to the ground. The circuit breaker near the fault disconnects the unhealthy part of the system so that the power doesn't go to the ground. It follows a different path. That's why the circuit breaker closes or isolates the circuit. The shorter the time to breaker operation, the better it is, and that time is known as clearing time. Okay, I told you generator angle can go beyond 90, but that's a limit. Before which the circuit breaker must operate. That is known as the clearing time. A 2-mark question can come in your exam. What is clearing time? Okay. In stability studies, the fault is assumed to be cleared by the time of the first closure. You might have seen auto recloser circuit breakers. Not seen, experienced. Power goes, suddenly comes back. Again it goes, again comes back, third time it goes for long time. So actually that is known as auto recloser. The circuit breaker tries again to see that if the fault is clear. If it is not clear, again it opens the circuit. So 2-3 times it does that. Okay. So I told you, you can estimate stability quantitatively by obtaining delta versus T equation and plotting it. Okay. So that is known as quantitative way, but that is a qualitative way, where you need not solve the equation. So that qualitative way is known as equal area criterion. So most competitive exams, including GATE, you will get questions on equal area criterion only. You won't get questions on numerical solution. Okay, that is part of PG syllabus. Okay, you will know only the essence of it. But this is very important. Equal area criterion is asked. Okay, so understand. So this is the concept of equal area criterion. It says if the generator is swinging, and it is approaching a condition where d by delta is equal to 0, that means it has reached the peak. Right? That means it has reached the peak. But if it is not encountering this d by delta is equal to 0, that means it is monotonously increasing in unstable case. So if this happens, it's a stable case. If this happens, it's an unstable case. Simply, the most simple way of saying it. Okay. So if delta t starts to decrease after reaching the maximum value, it is assumed that the system is stable. Thus the system becomes stable after some time if d delta by dt is equal to 0, and unstable if d delta by dt greater than 0 for a long time. That long time is known as critical clearing time. Okay, critical clearing time. Okay, maximum time d by delta can become greater than 0 is critical clearing time. Beyond that, this happens, generator can never come back to original position. Correct? Now we will derive what is equal area criterion. Okay. In exam, it can be asked as a theoretical question. So you will be asked what is equal area criterion or derive equal area criterion. Okay, long question. Yes.
So when we say it goes beyond where it can never come back, is that what we call desynchronized?
Yes. When it say it can never come back, that is actually means it will desynchronize for generators. Okay. For our case, instability means desynchronize. For a human being, when it goes, it cannot come back means it goes. That's it. Okay. For a generator, it simply means desynchronize. But that's a big thing. Desynchronized, one generator desynchronized can lead to cascading effect of multiple generators desynchronized, eventually leading to complete blackout. It happens sometimes back. It happens sometimes. Okay. So from the swing equation, d square delta by dt square, m d square delta by dt square, inertia into acceleration is equal to accelerating power p minus p. So therefore, this is equal to pa by m. Now, what do you do? Now multiply 2d delta by dt on both sides. Try to solve it. Multiply. Then when you multiply, you get one equation of this form. Multiply and integrate. Okay? You get this form. Simple. You multiply it so that you know differentiate what it becomes. 2d delta by dt. 2d delta by dt, right? You differentiate it is 2d delta by dt, right? Then the system is stable after some time if this integral is 0, or we have seen that if the system is stable after some time if d delta by dt is equal to 0, that you saw in the last slide. It means that this should be equal to 0, this integral, which eventually means. So you can write down the equal area criterion is mathematically expressed as, write down this equation. Delta 0 to delta 0 to delta PA d delta is equal to 0. So this is the mathematical form of equal area criterion. Mathematical representation of equal area criterion. Okay. Now, mane kono? Question that what is the meaning if you say it in words? What is the meaning? Okay. So it means that the system is stable if the area under the PA delta curve reduces to 0 at some value of delta. Okay. And it simply means the accelerating area must be equal to the decelerating area. So equal area criterion says the accelerating area must be equal to decelerating area. So whenever you have a problem with equal area criterion, either here or in GATE exam or any other competitive exam or engineering services exam, so So wherever there is an exam, always remember that you have to simply equate the areas. That's it. And you have to find out delta. Okay. Area you can easily calculate. It's simply integral of first initial point, final point, the equation into the variable. That's it. Okay. Now we will apply equilibrium criterion to various cases. Okay. We will see. So we'll see. First is sudden change in mechanical input. Okay. Sudden change in mechanical input. So it says, consider the system operating under a steady state operating condition. Pm0, Pe0, Pmax sin delta 0. Write down. Pm0 is equal to Pe0 is equal to Pmax sin delta 0. Okay. Now delta 0 is the initial operating point. Delta 0 is the initial operating point. Okay. Mechanical power input is equal to electrical power input. A stable condition, normal condition. Which is this? Draw graph. In parallel to draw it also. So initial angle is delta 0. Power is Pm0, which is equal to Pe0. And it must fall on the power angle characteristics. Okay. Now suddenly the load changes. There is a sudden increase in mechanical input. Okay. Pm1. So there is a sudden increase in mechanical input Pm1. How about so as you have seen, there will be an increase in mechanical power known as Pm1 minus Pm0. When initially it was Pm0. Now you have increased the mechanical input. Mechanical input can be increased. How to increase the mechanical input? Steam or water by opening the governor. Okay. So this is the accelerating power. This is the accelerating power. So because of this, the generator will accelerate. It will accelerate. Ideally, it should have reached point B. Ideally, it should have reached point B. But since it is acceleration, it will go beyond it. Go up to C. But then, if it is beyond B, then Pm1 will be less than Pm0. So there will be decelerating power. Okay? So there will be not less than Pm0, less than the electrical power. So it will be decelerating. So that means the generator will continue its acceleration and deceleration and finally settle down here. But according to equilibrium criterion, the total area under this curve must be equal to 0, which boils down to saying that the accelerating area must be equal to the decelerating area. Right? Now you will log to equate this. Find the equation for accelerating area and decelerating area, equate. Do it. Okay. So, for sudden change in mechanical input, two areas, accelerating area and decelerating area must be equal. Okay. So, accelerating power का कौन? Accelerating power is the mechanical power input Pm1 minus Pe0 or Pe. Okay. Causes the rotor speed to increase. At angle delta 1, Pi is equal to 0, but the rotor angle continues to increase. Okay. Pm is the accelerating power equal to 0. The equilibrium point in between, the equilibrium point, the mechanical input is equal to electrical output. Increased mechanical input is equal to increased mechanical electrical output. So it's B. But still, rotor angle continues to increase because of inertia. Pa now becomes negative. Then the accelerating power becomes negative. The rotor speed begins to reduce, but the rotor angle continues with delta. At point C, decelerating area A2 is equal to accelerating area A1, and the rotor angle begins to reduce, and starting point traverses the curve in the opposite direction. Under limiting condition, write down this. Under limiting condition, just write down this. We will explain this. Under limiting condition, Limiting condition माने maximum area. Okay, we'll show you the figure in the next slide. Maximum critical clearing angle. Okay, maximum angle to which it goes. That is known as delta max. Okay, so delta 2, the next angle will be delta max. That must be equal to pi minus delta 1. Okay, question we'll go to the next slide. This is a very important equation. Write it down. So this is the limiting case. This is the limiting case when delta 2 is delta max. Okay, critical case. Okay. Beyond that, beyond this, if the generator goes swings, okay, A2 will always be more than A1. Okay, A2 will always be more than A1. Or I think A1 will be more than A2. 2 also equal. So generator will continue to increase in this direction. Okay, it can never come back to the other side. So that's the limiting case. Note that the system will remain stable even though the rotor may oscillate beyond 90 degree. From our knowledge of steady state stability, we know that delta can be at most 90 degree. But in transient stability case, it's different. Okay, delta can go beyond 90. Just like sportsmen sometimes do things that for a normal human being is not possible. Running at a particular speed, jumping a long distance, but it can happen under certain situations. Okay, you might perform much better under stress compared to normal situation, just like that. So generator can go beyond 90 during faults, it can, but not permanent, for a very short duration. The condition delta equals 90 is meant for use in steady state stability, that doesn't apply to the transient stability. Remember, it's a very important point. Now we will compute the area. So what was the area? That time I told you to calculate. See, this is the answer. So A1 is equal to delta 0 to delta 1, PA1 minus PE d delta, which you can write in this form. Similarly, A2 is equal to PE, because after that point on which it decelerates, the electrical power becomes more. But the electrical output becomes more, mechanical input becomes less. That was never our operating point. So it reduces, it decelerates. Okay. So for that case, the area is this. Okay. For equal area criterion, this is the condition. So summary is for sudden change in mechanical input, the maximum clearing angle or the clearing angle can be obtained by equating the aesthetic area and hysteretic area, which can be obtained from the power angle curve, and eventually we get this equation. Okay. Clear? So all of you understood what is equilibrium criterion? Okay, so either it can be a derivation or it can be 2-mark question. What is equilibrium criterion? What is equilibrium criterion? What do you tell? What is equilibrium criterion? Accelerating area must be equal to decelerating area. Ethically mandatory. Ethically लिखिए ताकि आपको वो लिखो, तो उस सारे जाओ. Okay. So this completes essentially the topic of today's class. So I'll show you how to solve this. Now suppose there is a problem, how to solve this? Delta 0 means initial operating point that you will get from the P max side. So what it says, initially the power system transfer this much amount of power. So P max sin delta is this. So from that delta 0 you will get. But how to get delta max? Okay. Now this delta max appears everywhere. So the only method to solve it is using a iterative method. Okay, which is Newton-Raphson method. So this is Newton-Raphson method for solving this. Okay, I have given an example how to solve using Newton-Raphson method. So that means what you will do? You will give one initial, you will guess one initial value of delta max. What will be the initial guess? 90 degree or 80 degree. Okay, or even 110 also is fine, but always make it below 90. Okay, say 80 degree. Okay, then you iterate using this formula. So here is the last part of this module. Okay, and today we are going to solve this question. The generator supplies active power of 1 per unit for infinite bars to a lossless time reactance of 0.6 per unit. The reactance of the generator and the connecting transformer is 0.3 per unit. Draw this diagram, single line diagram for this question. Okay. So in this problem, first we will start with P max from the question. Okay, EV by X. Okay, that is the maximum power, and we know power transfer. I think in the question is given 1 per unit. So therefore, delta 0 we can find out the initial delta. Then we will guess what initial value of delta max. Okay, in radians, and continue the iteration using Newton-Raphson method. Okay, and we continue. Okay. So how it is solved using Newton-Raphson? So this is the form of the equation which can be implemented in Newton-Raphson. It's very not that difficult as we did in load flow. Okay, so we'll stop here. So this completes the qualitative aspect of transient study. Next class we will discuss critical clearing time and critical clearing angle. Stop.